Welcome and hello. This is a video exercise in HEC HMS, and in this exercise, we're going to be dealing with the gridded hybrid snowmelt method. All right, what I have on the screen here is an introduction to snowmelt calibration. This is the starting page, and I will leave a link to this page in the description. It'll be the first link. And what we're going to do here is download the initial files, create the meteorologic model, and then click a link and move on to a second page where we actually do the specific tasks related to gridded hybrid snowmelt method. All right, well, let's go ahead and get started. I'm going to scroll down just a little bit here. Click on this link here that says Upper Truckee River Start Zip, and then click the download button when that appears. There it is. All right, once that's downloaded, you can go ahead and just click the X to close. And let's leave the web page right here for now. I'm going to go ahead and open up that zip file we just downloaded. Here it is, Upper Truckee River, and then here are the files and folders we'd expect inside a typical HMS project. So I'm going to go up a level here, and then I'm going to find a place on my computer. I want to move those files. So I'll just drag those over, wait for that to copy. All right, that's done. Now I can delete the zip file. And let's go ahead and open up this project in HMS. So I'm going to go up to File, Open, and then click the Browse button. And now we'll find that exercise. And then here's the project. Here's the Upper Truckee River.hms file and select. All right, so our project is loaded. Right here up in the Watershed Explorer, we have our basin map, control specifications, and so on. I'm going to go ahead and expand the basin map just so we can see something here. All right, so I'll expand that. I'm going to go ahead and toggle off some of these layers. So view map layers. All right, that looks fine. In this basin model here, what we have is one subbasin and one sink element. So I can click on the map, get the parameters here for whatever element I click on in the components editor. In the components editor for the subbasin here, what I see here is a number of different methods. Hold on, let me toggle off the degree minute second option. Tools, program settings, and then I like to see it in decimal degrees. Okay, it's a little bit more compact that way. What I was saying is the snow method is what we're going to be focusing on. There are a number of different methods for snow, and we're going to be using this last one here, gridded hybrid, in this exercise. I'm getting a little bit ahead of myself because I also wanted to point out if we click on a subbasin, we also have some time series data that's associated with it, specifically the discharge gauge here at the outlet, as well as the snow water equivalent gauge, which is in the basin as well. So if I click on the subbasin and then I click on this options tab, I'm seeing the assignment of an observed flow, South Lake Tahoe, and then an observed snow water equivalent, which is this second time series data set right here. I'm only pointing this out because we're going to be using these for comparison after we set up our model, run the simulation, and then look at results. Also in the Watershed Explorer here, we have some grid data, and we'll be using these as well. This project was set up. It looks like it's 99% done. There's only a few things we need to do, and part of that is true, but it also makes sense to kind of save us time from doing a lot of the menial tasks, such as setting up these grids. Lastly, there is a terrain data right here, which is part of the model and was used to delineate the subbasin. All right, well, let's get back to the instructions here. I'm going to scroll down just a little bit. Here is a table that compares the three different gridded snow methods for a subbasin in HMS. We're going to be working with this middle one here, gridded hybrid snow. And what we see here is it just identifies a number of the different meteorologic components that we need to add. So the first task is to create a meteorologic model. Let me scroll down to that. So create a new meteorologic model and then parameterize it. All right, so back to HMS, what we're going to do is go up to the Components menu, Meteorologic Model Manager, and then click New. Now what we want to do is give it a name. We're call it Water Year 2017, and then click Create. I'll go ahead and close that. What that did was it added a meteorologic models folder up here in the Watershed Explorer, because this is our one and only MET model so far. So I'll expand that, click on the one we just created, Water Year 2017. Now down here in the components editor, I need to specify the different methods. So what it tells us to do in the instructions is to use US customary for the units. Shortwave radiation is going to be gridded shortwave. Long wave radiation is going to be gridded long wave. For precipitation, we're going to use the gridded precipitation method. And then for temperature, it's going to be gridded temperature method. So as you can tell, all of these methods are like the gridded version of that particular parameter. Also, we're seeing the icons up here in the meteorologic model as we select them. Wind speed will be gridded. There it is. Pressure is, we're going to use the gridded pressure. Dew point is gridded humidity. And then evapotranspiration is gridded Hammond. All right, now replace missing, we're going to change this to set to default in case any of our grid data has missing records. It won't stop the simulation and show us an error message. All right, I'm going to go ahead and hit save. And now for up in the Watershed Explorer, we need to actually assign the grid data that we've specified for that meteorologic model. So for instance, gridded shortwave and all these other methods would also have a grid name. Right now, by default, it's none. So I need to go ahead and make that selection. I'm going to use interpolated shortwave. For long wave, I'll click on that, assign the grid of interpolated long wave. Next up is precipitation. So for the grid name, I'm going to use the MRMS corrected. The reason I'm only seeing this grid is because this dropdown is only looking for grids of the precipitation type. So for instance, if I go to the grid and then I go to precipitation grid sets, there's only one precipitation grid set saved, MRMS corrected, and that's why it's the only one I'm seeing on this dropdown. Gridded temperature, let's add RTMA, wind speed, interpolated wind speed, gridded pressure, interpolated pressure, gridded humidity, interpolated humidity. And then for the evapotranspiration, it's just a coefficient, which is calculated using other parameters. All right, I'm going to go ahead and save that. Let's go back to our instructions. If we scroll down, we're told to choose a snow method. In exercise 40, we looked at this gridded temperature index. This is exercise 41. We're using the gridded hybrid method here. So go ahead and click this link right here, option 2. This is going to be the second link in the description of this video. All right, so what we have here is an introduction to the gridded hybrid method. The gridded hybrid snowmelt method is sometimes abbreviated RTI, which is short for radiation derived temperature index because it takes into account both the temperature and some other factors such as radiation, all of which are required in that grid data that we just assigned. All right, so let's go ahead and scroll down and start knocking out these tasks here. The first one is terrain pre-processing. So what we saw in the Watershed Explorer, at the very bottom, we have this terrain data layer that was used to generate the subbasin. And then inside that, here is our layer. What we're told to do for the first step is right click and then pre-processing slopes and aspect. So if it asks you, are you sure it's already been done? You can go ahead and hit continue. But if it hasn't been done already, it'll just start running automatically. Now that was fairly instantaneous, but the other step we have to do is also right click pre-processing solar shading and then go ahead and click continue if you want to wait 5 minutes. Since it's already been done, I'm not going to wait, but just so you know, the second step does take longer. So since it's already been done for us, I'm going to go ahead and click cancel. All right, the next step is to parameterize the gridded snow hybrid method. So what it starts us off with is telling us to make a copy of the existing basin model, give it this name right here. I'm just going to go ahead and copy that onto my clipboard, and then expand that basin model, set the method, and then go ahead and make the edits to the snow tab. So let's go ahead and do that. Back to HMS. Right here is our water year 2017 basin model. This is the one that we have up in view here. But what we're going to do is right click, create copy, and then paste in the name of the new basin model. RTI is the suffix here, or you can type it in. The description is optional. Click copy. And here we go. I'm going to bring that to screen. Okay, so here it is. I'm going to expand that and then just zoom in a little bit. If I click on the sub basin here, down in the components editor, we have all of our methods, some of which are already defined. Now, of course, the focus of this exercise is the snow method, specifically gridded hybrid. So go ahead and click gridded hybrid. That will give us a new tab in the components editor for snow right here. So go ahead and click that. And now the values that we want to type in here are almost all the same values as the instructions. So initial values will be default. I believe that's just 0, meaning that at the beginning of the simulation, at the beginning of the water year, it's going to be assumed there's no snow. If you go up to the control specification here and click to see the details, we see that the simulation is going to start on October 1st, which is the beginning of the water year. So it's probably safe to assume there's no or negligible snow pack at the beginning of the simulation. Okay, let me go back to the subbasin and then click on the snow tab again. All right. So the other values here are the same. We have 37.4 degrees for our rain threshold air temperature. Snow threshold air temperature is 30.2, 32.0072, 0.00011. I'm just double checking. This last one here is 3 for the water capacity as a percentage. So yeah, so it's 3 right here. Otherwise, everything else was already exactly as the instructions say. So I'm going to go ahead and click save. All right, the next task, I'm calling these tasks, is create and run a simulation. So what we have is steps 1 through 8, and that begins with creating a simulation run. Here is the name of it here. It's just Water Year 2017 RTI. So back to HMS, we're going to go to Compute Simulation Run Manager. I'm going to go ahead and click New. The first step here in this 4-step wizard to creating a simulation run is to type in the name. That's simple enough. Next. Now for the basin model, we're going to select this RTI basin model that we created and, assigned all of our snow data for. Next. This is the one and only meteorologic model that we created. And then finally, the control specification. All right, so I'm going to close that. Up here in the compute toolbar, I'm going to select our simulation and then click run. All right, that ran for me. Great. So let's go ahead and look at some results now. I'm going to click on the Results tab here in the Watershed Explorer, expand my simulation run, and then click on Water Year 2017 RTI. I'm going to look at the data for the subbasin, so I'm going to click on this Upper Truckee River S10 subbasin. Give myself some more room here. What I want to look at is the observed snow water equivalent, and then I want to scroll down and then click on the snow water equivalent right here by holding down Control, single left click. I have a little preview down here, but it's easier to see the plots if I actually click on the graph tab up here. All right, let me move that over and then add some colors so I can see it a little better. What we have here in red is the observed snow water equivalent. And then in the blue line, this is the computed snow water equivalent from the simulation. As you can tell, our computed results are less than the observed data, and this observed data in red is assumed to be the target data, or the values that we want our simulation run to generate based on all of the inputs, most notably the parameters for the snow method. All right, so what this tells me is we need more snow. We need a larger snowpack. And this right here is a time series, so I assume it's the average snow water equivalent over the entire subbasin using that grid to point calculation. Before we move on, I did also want to point out a few things. For instance, if you do a right click on the subbasin in the map, view results snowmelt graph, this brings up the same plot we just saw in the bottom panel, but there's also at the top and middle panel, we have a hyetograph for precipitation depth, as well as air temperature in this middle panel. So it's just a quick way to be able to bring up the results without having to click into the results tab and find the exact data you want. If I click on the subbasin here and then click on the options tab, which is right here, we have the observed flow for South Lake Tahoe, as well as observed snow water equivalent for that subbasin. These are both time series data sets. So what we saw in that previous graph was the snow water equivalent plot. Here, this was the red line versus the computed snow water equivalent. And then this observed flow is the observed flow rate at the outlet of the subbasin, at this sink element right here. We can also look at that comparison. And it's actually easiest to just click the sink element and then view graph. That's what this graph is right here. So the black line here is the observed time series data for the flow out of the subbasin, and then the blue here is the computed. As you can tell, this is a pretty good fit, at least in some places. Let me zoom in a little bit here. Here are the two lines. The blue is the computed from the model, and then the black is the observed. So it's let's see, I got to pan up a little bit here. Yeah, so we're definitely off on that peak there at February 10th. And then later in the water year, it looks like we're off a little bit. All right. One final plot before we get to the calibration is not a plot at all. It's actually a graph. It's this global summary. I actually like to click on the subbasin and then click on the global summary table. And what we're seeing here is the computed results. And then below that, observed flow and observed snow water equivalent. And basically how our computed results compare to the snow water equivalent and the discharge. Next up in the instructions, we're told to calibrate the gridded hybrid parameters, and it gives us some suggestions here. In step one, it tells us we should be changing these temperatures to 35 degrees Fahrenheit, and then rerun the model, and then look at the results. After that, it tells us to do a couple other steps. So let's go ahead and do that first one. I'm going to go to the snow tab here for my sub basin, and then change these temperatures to 35 degrees Fahrenheit each. All right, so I'm going to save that, run the simulation. All right, the simulation has completed. Let's go ahead and look at our results again. I'm going to click on the observed snow water equivalent and snow water equivalent right there, and then click on the plot, and that looks a lot better. Here I see the two plots lined up almost perfectly. This is a very good fit for snow water equivalent over the course of the simulation. If I go ahead and zoom in, we can see that it's just a very good fit. Maybe a little bit of an over prediction in the first few months. Probably the best fit I've seen for snow water equivalent yet. If I click on the subbasin in the map here, and then I click on the global summary table, what we see is a Nash-Sutcliffe score of 0.994, and the best you can do is 1.0. And this is a score that's, I think, sometimes difficult to achieve. So that was for snow water equivalent. For the observed flow, it's only 0.512, which is definitely not as strong as 0.994. And then we also have percent bias values as well. In step two of this final task of calibration, the instructions tell us to change the melt factor, first to decrease it to 0.0035, and then later to increase it to 0.01 in an attempt to better match that snow water equivalent time series with the observed. So I'll click on the snow tab here, and then this is what it's talking about, this melt factor. So 0.0035. So I'm going to go ahead and save that, and then let's run the simulation. All right, the simulation completed. Let's go ahead and take a look at the results. You know what I'm going to do is just right click and then view the Snowmelt graph. And from this graph already, I don't need to open up the details. I can tell that this is not nearly as good of a match as we saw with the previous settings where we had the original melt factor of 0.00722. If I click on the summary table, I can again see that the Nash-Sutcliffe score dropped off dramatically. So the change we made there was not the one we want to make. The instructions then tell us to change this melt factor to 0.01. And then I'm going to hit save and simulate. All right, the simulation completed. Let's go ahead and let's just right click and then view the results this way. Snowmelt graph. Okay, as before, the snow water equivalent is not as strong as our second trial. I'm calling this the fourth trial now. It was probably a little bit better, but I think it's best to leave that melt factor at the original value of 0.00722. So I'm going to go ahead and change that back. This is just the nature of calibration, especially when you're doing a trial and error method like I'm doing here. The instructions go on to tell me to continue modifying other parameters and running simulations and viewing results. So it's referring to the max negative melt factor, ATI coefficient, wind function, and so on. I can also change the temperatures a little bit if I want, but I think the temperatures at 35 is a pretty good match, at least for snow water equivalent. As far as the discharge gauge, I can go ahead and view that graph. And again, I'm not seeing a perfect match here, and that's reflected in those statistical metrics that compare the two and the goodness of fit. So maybe changing some snow related parameters will improve that, but also there's a lot of other parameters such as base flow, loss, transform, and canopy. All these methods have their own parameters, which may more likely affect and help us match that outflow graph. Here is the final summary table for our fourth trial and the data and the parameters here. So I'm going to go ahead and close that and then conclude by summarizing with this Excel table, which shows the results from our four different trials. Over here on the right, these columns here show us the input data, at least the data that changed over the course of the simulation. For trials 1, 2, 3, and 4, this is just trial 1 here, and then here are our values. I'm particularly looking at the Nash-Sutcliffe value for this snow water equivalent, column 7. So this is trial 1. For trial 2, we changed the temperatures to 35 degrees Fahrenheit and got our best snow water equivalent score. On trial 3, we increased that melt factor. I'm sorry, we decreased the melt factor, and then all of our numbers worsened. And in the final trial, we increased the melt factor. So I still think this second trial here with the 0.0072 melt factor was best for us, and that's reflected in our best numbers here for both percent bias and Nash-Sutcliffe. Well, that's it for this exercise where we investigated and calibrated the gridded hybrid snowmelt method in HEC HMS.